So now, which all transistors do we need to worry about swing at all, swing limits? Which of these transistors do we need to worry about? Okay, let's start from the left. This guy. Well, the incremental voltage is 0. The incremental current is also 0. So it doesn't change at all. So that we are fine with. What about this chap here? We need to worry about it or no? Why? Why is there no incremental voltage across the transistor? So what? What about VDS? Is the VDS constant or is it changing? You can safely ignore only if the incremental VDS is 0 and the incremental VGS is 0, which is equivalent to saying incremental current is 0. Yeah, so we need to worry about that character. What about M1? Do we need to worry about it or no? We need to worry about it because the gate is jumping up and down, whereas the drain is at a constant potential, right? So we need to worry about the transistor getting into the triode region. Okay, so M1 we have to worry about. What about M2? M2 also we have to worry about. What about the PMOS loads? What about the one on the left? The diode connected PMOS load. Why? The source drain voltage is not varying at all, right? But what about the incremental current? Is there a possibility that the transistor goes into cutoff? Is everybody clear that this transistor is not of concern at all? What about the other transistor on the right? The incremental voltage, the drain is 0, so basically VDS is not changing. Incremental current is 0, current is not changing. Therefore, this we don't have to worry about this as far as swing limits are concerned, right? Okay, what about the next transistor, this guy? The drain is swinging, so we basically need to worry about that chap. What about the tail current? The current I2, current source transistor I2. Yeah, yes, we need to worry about it. What about the output stage? So the drain source voltage is changing or the gate drain voltage is changing. What about the I3 transistor? Change. All right. What about the currents through any of these transistors? What is the current flowing through? What comment can we make about the current through any of these transistors as Vi is changing? So this incremental current is 0 anyway. M2's incremental current is also 0. The tail current's incremental current is, this incremental current is 0. This incremental current is 0. This incremental current is 0. What about this incremental current? 0. This incremental current? 0. This incremental current? 0. This incremental current? 0. So what does this mean? The currents are not changing in any of the transistors in this particular circuit. So what does that mean? So we don't have to worry about the cutoff limit at all for any of the transistors, right? So your job has become easier by a factor of 2. All right. Now there is no magic to it. I mean, of course, if you can look at the circuit and figure out which is the problematic transistor, I mean, good for you, right? Otherwise, we simply go transistor by transistor and figure out what the limits are. Okay. All right. So let's start with M1 first. Let me label the devices: M2, M3, M4, M5, M6, M7. So M1, what is the triode limit? How high can the gate go before M1 goes into the triode region. What is the drain potential? Drain potential 3.8. So, what is the highest voltage that the gate of M1 can go before M1 goes into the triode region? It is basically 3.8 plus 1 Vt, which is 4.8, right, which is nothing but Vi, which is 2.5 plus A, which means that A max is, as far as M1 is concerned, A max is 2.3 volts. What about M2? Well, M2 is the same, A max is 2.3 volts. M3, what happens? Is M3 in trouble when A is positive, or when in the positive half of the input cycle, or the negative half of the input cycle? When the input goes down, this common source node also goes down, and therefore you are in the danger of M3 going into the triode region. Is that clear? So, what is the lowest that so the voltage, this lowest voltage at the drain of M3 is nothing but 1.3 minus A, 1.3 minus A max, which must be equal to, and what is the smallest voltage that you can have between the drain and the source? Drain and the source. This is the overdrive voltage, which is 0.2 volts, which means A max is 1.1 volt. Okay. What about M4? What is the highest the drain can go to? So, that is 3.7 plus A max must be equal to 4.8, which implies A max is 1.1. What about M5? What is the lowest voltage that the drain of M5 can go to? That is basically 3.7 minus A max must be, which must be equal to 0.2 volts, which basically means that is 3.9 volts. Sorry, 3.5. M6 is, so is M6 in trouble in the positive half of the input cycle or the negative half of the input cycle? When A is positive, the gate is going up, whereas the drain is sitting at the same potential. So, the transistor is going closer towards the triode region. So, for M6 it is 3.7 plus A max. What is the highest it can go to? What is the highest the gate of M6 can go to before the transistor gets into the triode region? Pardon? The drain potential is at 5 volts. So, how high can the gate go? Yeah, so that is 6 volts, which means that A max is 2.3 volts. All right. about M7? 2.5 minus A max is the lowest that the drain potential can be. This must be equal to, so A max is nothing but 2.3 volts. All right. So which which of these things do you think is the most problematic? So you basically say that the two transistors M3 and M4 basically go into the triode region at exactly the same point in this particular circuit, and therefore A max is the minimum of all these voltages, and that's basically 1.1. As you can see, there is no rocket science here. This is the same thing that we have been doing for all the single transistor circuits. First job, find the operating point, then replace all transistors by their incremental equivalents and do the small signal analysis. Once you do the small signal analysis, you can find the incremental voltages everywhere and the incremental currents in every transistor, and then you know the quiescent value, you know the incremental value, so you can find the total current in every device and the total voltage in the total gate source voltage in so total gate source voltage is total drain source voltage everywhere. With that, you can go and find the swing limits for each transistor, right, and therefore you can find the swing limits for the entire circuit. Okay. With a little more experience, I mean, if we didn't kind of here we were already able to see that 3 of the transistors don't contribute at all, right, and for the other transistors which can potentially mess you up, we saw that the cutoff limit need not be checked in this particular circuit, right. So if you stare at it, more pieces of information will fall out. For example, we are only interested in the transistor going into the triode region. One thing you can notice is that the voltage at the drain of M3 is 1.3 plus Vi. The other one here is nothing but 2.5 plus Vi, correct. So which do you think is more is deeper in trouble? So then does it even make sense to consider M7? Yeah. So basically, before M7 goes into trouble, you can know that you're already finished, right. So there is no point in considering M7, right. So therefore you've you now reduced your job to finding the stuff for 1, 2, 3, 4, 5 transistors. What about M5? Yeah, well, if M7 is not in trouble, then M5 is definitely not in trouble, right. So you can remove that guy also. Okay. So just like I said in your lab experiment where 10 guys are sitting around doing one experiment, right, the only fellows doing work are 1 or 2 chaps, right, all the other guys are just there, what do you call, to bring tea and tell you what you missed in Kapil Sharma comedy show the previous night. You understand, right. So you can see here that only the 5 transistors that cause potential problems are M1, M2, M3, M4 and M6. In fact, M6 can also be eliminated. Why do you think so? What is the voltage across what is the drain source voltage of M6? The drain is at 5 volts, the source is at 2.5 plus Vi. So the difference is 2.5 minus Vi plus Vi does not matter. So it is 2.5 minus Vi, right. So if so M3 or M6, which one is the drain source voltage of M3 is 1.3 plus Vi, The drain source voltage of M6 is 2.5 plus Vi. Which one is going to be in trouble first? M3. So, there is no point in even considering M6, right, alright. So, with a little bit of experience you will be able to just simply throw away a majority of the transistors and only look for a small subset of transistors is basically what is going to limit your speed. You understand, right? But if you do not practice enough and basically you are stuck in an exam, the sure shot way in which to do the problem is to one observation I would like to make is that nothing here is arbitrary, right. There is a reason why every transistor is there, there is a reason why every transistor is sized a certain way, there is a reason why every transistor is chosen to be the type it is, okay, alright. I mean just like if you buy a car and you open up the hood, right, there is a reason for every part that is there, okay. The automobile manufacturer is not trying to confuse you by putting like 4 boxes there which do not do anything, correct, okay. Same thing with circuits, alright. And I do not know if some of you are exposed to the 741 op amp. How many of you have seen that in your undergrad at all? If you have, you have seen, okay. So, alright, and that circuit looks as you can as you will probably agree, looks a lot more complicated than this one, right. We will eventually get there, but for starters this is a good starting point, and this is a very commonly used circuit for CMOS op amps. And the only thing that is left to be solved is that as we discussed, one of the problems with having multiple stages is that it turns out as you can imagine that nothing in the world is instantaneous, correct. So, it is not that one problem with our model for the MOSFET is that we assume that you apply VGS immediately drain current will flow, right. It turns out without any going into any detailed physics, if somebody told you that you apply a voltage and instantaneously current starts flowing, you will say nice try, correct, okay. So, there is always every stage, every transistor is associated with a delay, right, in vague terms, okay. Now, to get gain, what are we doing? We are taking, so each amplifier stage has got some delay. When you cascade amplifiers, you get more delay. You get why did you cascade amplifiers in the first place? To get gain, correct. But along with gain comes delay, right. If you want more gain, you get more delay, right. And now, if you attempt to close if you have a negative feedback loop with a lot of delay in the loop, all right, what will potentially happen? Not what infinite time, I am telling you there is only finite delay, no. You have a feedback loop and there is a lot of delay. For example, in an exam, quizzes and in a course, quizzes and mid semester exam and assignments etc. are all basically for your feedback, correct. So, what if I decided to kind of give you graded papers, I do not know, 2 years later. So, basically you do not know, hopefully you should, but because if you do not get your marks, you do not know whether you understand the stuff or you do not, correct. So, similarly, regarding say complaints, right. So, let us say something is not working for you in the department, right. So, your first step would be to go and complain to your faculty advisor, right. Then say nothing happens, then that is only one stage of gain, correct. Then you go and complain to the head, right, that is 2 stages of gain, right. So, you complain to the faculty advisor complains to the head, now then nothing happens and then the head complains to the director, right, that is 3 stages of gain. And so, as you can see, each stage takes time, right? Okay, all right. And if that doesn't work, you go complain to the Prime Minister's office, and that's like you know that the gain from there to here is like infinite, right? But the delay is so much delay, all right, that if you hope that the Prime Minister is going to solve every one of your problems, I mean nothing is going to happen, correct? So if you have a negative feedback loop if you have feedback loop with a lot of delay, what will happen? Yeah, so when the feedback has come, that's corresponding to the feedback is based on the input like 3 years ago, all right, and now things have changed completely, but then the feedback says no, you do this, but then you say, well, no, I solved my problem 3 years ago, then the feedback doesn't know that, says no, never mind, you do it anyway, right? And then your error goes completely in the opposite direction, right? And so there's basically going to be instability, correct? Okay, I mean a simple thing that I'm sure all of you have experienced this with online classes and stuff like that is what? So well, if the teacher has got speaker phone on and what do you call? Of course, his mic is on, and the student has got mic on and speaker on, then what do you see? Well, you see, I mean, if the system is marginally stable, you will see the teacher says hello, and then you see hello, 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 right? Right? If the gain is too much, you will see, I mean, the whole thing you will see is the whole system starts singing, correct? Okay, all right. And the more the delay in the network, you will find that the frequency of oscillation is lower. Okay. All right, feedback loop is closed through base station, Airtel, maybe with Zoom it's going to Europe and coming back, and like the loop is closed that way, but there's a lot of delay in the whole process. Okay. So whenever you have a high gain negative feedback loop, you have to always worry about stability. Nothing comes for free. All right. Okay. So in this attempt to get more and more gain, you pay the price you're paying is that you're picking up more and more delay, and when you close the loop, you get more and more. You get this. You end up with this potential for instability. All right. So this basically is all I had to say about the DC properties of a two-stage. This is a two-stage operational amplifier, right? And I mean, if in many cases the gain may still not be sufficient, can you simply tell me a simple or rather a straightforward way of increasing the gain by another factor of GMRO without adding another cascaded stage? No, the M6 is there to give you low output resistance, right? Yeah, so that doesn't work. Why are we getting, okay, let me give you a hint. What is the gain of this stage? Minus GMR. So, I mean, if you want to increase the gain, you either increase GM or you increase RO, right? Okay, how can you increase RO? Cascode, right? So basically, an improvement over this is basically to add a cascode here. Okay, and one way of biasing this node is to simply do that. Correct. We have seen this in in the class as well as in your tutorials, right? So this is a cascode. What is the output impedance looking in here? GM. GM R naught square. All right. So what comment can you make about the looking impedance up this way? I mean, let's assume that this is biased appropriately. so that the transistors, all transistors are in saturation. What is the output impedance looking up? Gm R naught square. And so what is the, so if you look at the second stage, what is the gain now? Incremental gain. Let's take a look at the stage again. This is VDD, this is appropriately biased. All these are bias voltages appropriately chosen, right? That's what this means. So what is the question is, what is the incremental gain? So what do? We find the Norton equivalent, correct? So if we find the incremental equivalent, this becomes ground. To find the short circuit current, we connect Vi to incremental ground and measure the short circuit current. What is the short circuit current? This is Vi. What current? What is the incremental current flowing there? Pardon? Why? Yeah, so the VGS of all these transistors is 0. So basically, this incremental current is 0. When we put Vtest here, the incremental current here is 0. What comment can you make about the incremental current there? This is basically nothing but a common source amplifier feeding into a common. We discussed this in the context of a cascode before. What is that amplifier? Did we discuss the cascode clearly? Yeah, so what is the, it is a common gate amplifier. So what comment can you make about the incremental current here? That incremental current is Gm Vi. So what is the incremental current here? Gm Vi. So what is the Norton short circuit current? Yes, people. Yeah, so this Gm Vi flowing in that direction. All right. So what is it? To find the Norton resistance, what do? We basically ground this. Okay. So what is the output resistance? It's just the parallel combination of these two output resistances. Basically, it's roughly of the order of Gm R naught square by 2, assuming all the Gms and Ros are the same. So what is the gain that you get? Gm R naught the whole square by 2, the negative sign. All right. So you get, so what is the gain of the total operational amplifier? Yeah, so basically you get GMRO something of the order of GMRO the whole cube, right? So if the gain is of each stage is, say, if GMRO is, I don't know, 30, 30 cube is some 27,000, right? Okay. Last piece of the last question before I conclude this stuff on op amps. Remember when, so this, let me abstract it out as a current source I2. So we said, well, the gate voltage here is simply nothing but, whatever source gate voltage is needed to support a drain current of I2, right? But we also had this discussion where we said that you cannot force current into the drain of an op amp, into the drain of a transistor and expect the gate source voltage to develop. But that's exactly what we are doing. What is the meaning of biasing is proper? Alright, think about it, we will talk about it in the next class.